of A, while A is a regular element, is regular is. Similarly, every element of R class of A is regular. Now we show that every element of D class of a regular element is regular. So we prove this result for D class. So that's why it's called regular D class, because either every element of D class is regular or every element of D class is not regular. So in that case it is called irregular D class actually. So let's try to prove this. Every element of D class is regular if it possesses only one regular element. Then every element of that D class is the regular. So let S be a semigroup. Let S be a semigroup, and A is a regular. Is a regular element of S. Then every element of D class of A is regular. Every element of D class of A is regular. Solution. Let's choose any element. Let X be in the D class of A, which implies X is D related to A. So, but D is the composition. Actually, this means X is as a composition or related to A. So that means there exists some element C in S such that X is related to C and C is or related to A. So this means X belongs to LC, L class of C, because it's related to C, and C belongs to R class of A. C belongs to. Now what's A? A is actually a regular element, so that means every element of R must be regular by previous exercise. So that means C is regular element. And if C is regular element, then every class of LC is regular, which means X is a regular element. X belongs to LC and it's a regular element. So which implies by previous exercise, X is regular as C is regular. As C is regular, because C belongs to R, and A is given regular, is given that this is a regular element. So that means if D class contains a regular element, then every element of D is regular D class. And in that case, we call this D class a regular D class, if every element of D class is regular. If every element of D class is regular, then we say D is a regular D class. Otherwise, it's called an irregular D class. And one more thing, if it is a regular element, then it's called a regular element, and if it's not a regular element, then we call it irregular element. Okay. Now, idempotent is always regular. Idempotent is always regular because if he is an idempotent of a semigroup S, so E of S means the set of all idempotents of S. So if it has say 3-4 elements in E of S, then E of S is consisting of those 3 elements, which are idempotents. Okay, E is an idempotent of S, so means that E belongs to E of S. E of S means the set of all idempotents of S. Okay, so if E is idempotent of S, then E into E, which is equal to E square into E, but E square is E, it's E into E, that's equal to E square, which is equal to E. So that means E is equal to E. So which means for this E, there is E, such that E is equal to E, which implies E is regular. E is regular. So that means if D class contains an idempotent, if D class contains an idempotent, then every element of D class, element of D class is regular because it contains idempotent, and idempotent is regular. So if it contains one regular element, then every element of D class is regular. So therefore it's a regular. Therefore it is a regular D class. It is a regular D class. So if you have some D class, say that's D is a D class. If that D contains idempotent, then every element of that D must be regular because E is regular. And in that case, it's called a regular D class. So let's try to find its sort of inverse. We will see that if a regular D class, if we have a regular D class, then it must possess possess some idempotents. Must contain some idempotent elements. Every idempotent element is regular, but every regular element need not be idempotent. But in case you have a regular D class, every element of regular D class is regular, and we will show that some regular elements are actually idempotents in that regular D class. Let's try to prove this theorem. So let me first state this theorem, then we will prove it. In a regular D class, in a regular D class means it's a D class in which every element is regular. Each L class and R class contains an idempotent. So if each L class contains idempotent, then D class also contains idempotent because actually D relation is a join of L and R. So then each L class, then each class and each R class contains an idempotent. Contains an idempotent. Okay, let's try to prove this theorem. So it's a regular D class. We need to show that each L class and each R class contains an idempotent, and we know that every D class is actually union of L classes. In fact, let's choose a regular element in D class. If A is a regular element, if A is a regular element in a regular D class, then there exists X, because it's a regular element, there exists X in S such that AXA is equal to A. So now look at this. We have a X times A equal to A AX and we have so AX times A, or you can say A times AX times AX on left side, AX times A is equal to A. Then this XA AX again this AX is equal to AX, but this AX should be on. How do we do it? So let me see this. Let me write here this A times X equal to A, and let's look at this. A times XA, so A times XA, okay, A is an element. Now again this X times A equal to XA. So this means that this XA A times XA is equal to A. So that's your element XA. It exists here. So that means what's A, and X times A equal to XA. So that's the second element. That's the first element. So can I say this is related to XA? Because there exists A and X such that A times X equal to A. There exists A. So yes, it's okay because we have two elements XA and A, so they are actually L related to each other. XA is L related to A, so which means since this D is so is a regular element in D class, so is you have chosen A, any element in a regular D class, or you can say in L class as well. So actually you have to show that every L class has an idempotent. So LA is an L class, so it's in any L class here, so it possesses and it has an idempotent which is XA, so which means that XA, it belongs to L class of A, and this XA is idempotent. Why it's idempotent? Because you can see XA into XA. Here you can see AXA is equal to A, it's XA. So XA whole square is equal to XA. So that means the every L class has an idempotent XA. Is an idempotent of L class. So here this X is R related to A, because for R related so similarly you can prove each R class contains an idempotent. So now X is R related to A by definition. How it is R related to A? If you want to verify it, what are the elements are those U and V. So XA is R related to A if and only if there exist U and V such that U times XA equal to A and V times X equal to XA. And you can see that in this case our U is A and V is X. Okay, so that means XA is related to A, so which implies this XA belongs to L class of A, and this X is actually idempotent because AXA equal to A. So from this you can conclude that XA whole square is equal to XA. Okay. So on similar lines you can see this that you can prove that every R class contains an idempotent. Now next result is that's again very important. So in this result you have seen that if AXA equal to A, then X is L related to A, and X is idempotent actually. Now we have next theorem that is every idempotent E in a semigroup S, every idempotent E in a semigroup S is left identity of R class of E and write identity of L class of E. If E is an idempotent in a semigroup S, then this E, it is left identity of RE and right identity of LE. So let's try to prove this. Choose any element in that A belongs to R. Okay, R class of E. So which implies A is R related to E. So that means there exists X, Y in S1 such that it's right, it's A, X equal to E and E, Y equal to A. Now I want to prove that this E, it's actually left identity of RE. So now A times E times element of RE, it should be equal to A element of RE. So let's see this. It's equal to E into A. What's A? A is EY. So it's equal to E square Y. That's it should be equal to A actually. It should be equal to, yes. It's equal to A square Y since E is idempotent. It's EY and EY is equal to A. So therefore EA is equal to A for all A belongs to RE, which implies E is left identity of RE. Similarly, E is right identity of LE. That can be proved on similar lines. Okay. Now let's state the following theorem. One more thing that we should have mentioned here, the notation actually. VA, it denotes the set of all elements which are inverse of A. So it's those elements A dash in S such that A dash A equal to A dash A dash equal to A dash. So VA means the set of all inverse of A. In case of groups, VA is singleton set because every element possesses unique inverse. But in case of semigroups, this set may be empty or this set may contain more than one element. So VA means the collection of all inverses of A. Now we have following theorem. Let A be an element of a regular D class D. Let A be an element of a regular D class D. This is a D class in a semigroup S. In a semigroup S. Then following hold. First part, if A dash is an inverse of A, if A dash belongs to B of A, then this A dash is also in B. A is in D, okay. A is in this regular D class D, A belongs to D, then we need to show that if A dash is an inverse of A, then A dash is also the member of D. So that means D is actually closed with respect to inverses. And the two H classes and the two H classes which are R class of A intersection L class of A dash, comma L class of A intersection R class of A dash contains respectively the idempotents. Contains respectively the idempotents A dash and A dash A. This we have seen in the previous theorem that XA, here XA in place of XA, because at that time we have AXA equal to A. So in that case, so this A dash of A is what it was actually there XA. So here it's A dash A, and XA is actually the idempotent of LA, and also it's an idempotent of RA dash, that you can easily verify. And similarly, this AA dash, it's an idempotent of LA dash and RA dash are respectively the idempotents. These two edge colors, they contain these idempotents. That follows from previous theorem. You can easily do it. And it's a second part. Second part is if B is in D, if B. Second part, if this, if B belongs to D, that's D class, it's a regular D class, which already contains A. So B and D are appear later. Is such that RA intersection LB, RA intersection LB, and LA intersection RB contain idempotents E and F. Contain idempotents, in that case A dash and A dash A, they are actually idempotents. Now they contain suppose idempotents E and F. Then actually they are of this form actually, you need to show that. So in first part the idempotents are A dash and A dash A. Now in that case, suppose they contain the idempotents E and F, then you need to show that these idempotents, they must be of this form, A dash and A dash A form. Are idempotents respectively are idempotents respectively, then HBB class of H contains an inverse, A star of A such that the first idempotent E, it's equal to A star, such that A star is equal to E and A star A is equal to F. It is some sort of converse of this first part. In first part you will see that A dash and A dash A, they are idempotents of these two